I see everything okay?
Yep, I can.
Fab. Cool. So guys, welcome to the support vector machine chapter. As I was actually mentioning to Aoife before you dropped in, Corey, I felt like I sort of lucked out, so to speak, with this chapter. Not because it was easy per se, but I felt that the concepts were fairly intuitive. I don't know about you guys. And it wasn't particularly lengthy. So as you can see here, I've kind of given a hard stop for today's discussion around the soft margins slash support vector classifier. But of course, if you guys want to like delve into more discussions, we can for the hour. And next week we can anticipate to delve more into like support vector machines themselves, quadratic decision boundaries when things are non-linear. That's how I divvied it up in my head, at least. But to start with, we'll just set the scene a bit. Support vector machine chapter, we examine ways to classify data based on the supervised learning algorithm, which tries to find a best boundary, which we call a hyperplane, to separate different classes within our observations, our training observations. So defining hyperplanes according to the book, which I thought was actually very helpful just from a conceptual standpoint. We're probably all familiar with hyperplanes, as we can see here, from a literal line perspective, in that in a two-dimensional space, a hyperplane looks like a line. And because hyperplanes can be defined as p-1, in a three-dimensional space, hyperplanes then become a plane, and so on and so forth. And obviously, as p increases, it becomes a lot harder for our minds to conceptualize a hyperplane and what that looks like mentally. But nonetheless, you can still apply that principle in those frameworks as well. And this is the general p-dimensional case as defined by the book. So the reason we set the scene here is because we're actually going to be implementing hyperplanes in how we classify these data observations. And in this case, we call them a separating hyperplane, which is very imaginatively named. But imagine you had a lot of data and you wanted to place data observations as to whether the data was cats or dogs. Your separating hyperplane would basically help you identify where those data observations were placed in your space. So as the name suggests, the line separates the classifiers by a line. Like I use the example of cats and dogs here. I was watching a lot of cat meme videos this weekend, so use that example quite well. And let's say we want to be able to develop a classifier based on training data so that it can correctly classify test observations given these feature measurements. So you have a lot of data with features like ears, eyes, snout size, meow, woof, and you want to be able to place this data accordingly in a region. So if we do have a separating hyperplane, we can use it to assign test observations to a certain class of your data, depending on which side it's located of the according to the hyperplane. So like I said, you might assign cats to one region, while another portion of the grid might be reserved for dog. And we'll see later down the line, obviously, especially next week when we go into more non-linear decision boundaries, how this can be really useful and how this can help us classify our data. But of course, obviously, the question here now is, how do we actually decide upon which separating hyperplane is suitable for our data? Because in the book, as it rightfully states, essentially you have this line, or this plane rather, this hyperplane, and let's say hypothetically you were to shift it tiny amounts, there would be an infinite number of cases by which that hyperplane, that separating hyperplane, would be moved but not touch or broach upon your data points. So we have an infinite amount of opportunities to choose from in terms of which hyperplane to use for our classifier. So we need to know how to decide that. So to do that, the book suggests a way of applying the maximal marginal classifier to address the optimization problem, i.e., which hyperplane do we use, like which is optimal. And one way of doing this is applying what's called the maximal marginal hyperplane. And in short, that is the separating hyperplane furthest from our training observations. So you don't want one essentially too close to a data, an observation. That would not be a marginal hyperplane we would want. We want the one that's furthest away. And in an effort to then classify these test observations based on which side of the hyperplane they lie. So let's have a look at a bit more in more detail of this optimization problem. And we're going to have a look at some of the mathematical notations. So to calculate our maximal margin hyperplane, we literally compute the distance from each training observation to a given separating hyperplane. So you can actually see here as well, like the intercept and the coefficients of the slant or the tilt of that line, which I thought was quite a nice way of visualizing it. And the smallest such distance can be described as the minimal distance from the observations to the hyperplane, which is what we know as the margin. And this little m, this margin, is going to be very important for when we look at the non-separating cases and how to decide which side of the plane or hyperplane that a data point lies. But for now, I think what was quite interesting in the book that maybe we can discuss is thinking about like the purpose of the constraint here in the maths, and thinking about how, as I said before, with this m value, or this margin rather, how can we verify that our observations are on the correct side of the hyperplane, like where we want, let's say we want the cats to be on one side or the data point dogs to be on one side. So I don't know what you guys thought. I mean, obviously it says in the book, but what your thoughts were. And if you guys have had any practical use cases of data where you've applied this classifier at all.
Well, I certainly have it. And so I only kind of looked at, I haven't dived as deep into this as I would like, but what is the constraint exactly? It's you want to maximize or minimize the distance. Okay. And so how's the constraint expressed in that that second equation?
Yeah, so I
Okay.
think, yeah, I think the constraint basically requires that each of your I mean, I could be wrong, but it could be that your each observation has to be on said a correct side, whatever that be.
Mm-hmm.
Providing that, obviously, I think providing that m is positive, I think.
Mm-hmm. Okay, interesting.
But again, I could be wrong, but that's
yeah, you basically just want to that equation and the last one there is, I believe, like the equation of the hyperplane.
Yeah.
So if you have a point somewhere in your vector space and you fill in the coordinates of your point to that equation, if it equals 0, that means your point is going to be on the hyperplane. And then greater than or equal to m is the margin, is it?
Yeah.
Okay, so yeah, I guess you want your points to be at either side of this margin, so you have your hyperplane, and then you have this margin and your points would be outside of the margin. So none of your points would be between the hyperplane and the margin. So m would be positive or negative, would it? Depending on which side of the hyperplane your point lies.
Yes, I think so as well. Yeah.
I don't know, that says greater than or equal to m, so maybe
greater than or equal to, yeah.
And did you say m had to be positive?
Well, the book says that the mentions that the constraint actually like requires that each observation is on the correct side. But again, this is a constraint rather than the equation itself. Sorry, not the margin itself. Let me have a look. So yeah, I think it does need to be positive.
Yeah, it says that if it's positive, that means that it's on your point is on the correct side.
Yes.
So I guess it's relative to where your point should be.
Yeah, that makes sense. That makes sense. So that, yes, that answers that little discussion point of verifying observations on the correct side. But yeah, I felt that this was not super reminiscent of logistic regression, but I think there are some flavors maybe that, especially later in the chapter, I think it's a bit more reminiscent, but I thought that was of note. So this is obviously very helpful in the use case that we can separate data perfectly into these with this classifier, and that we can. I mean, what was interesting to read as well is that I believe the maximal margin hyperplane depends directly on only a small subset of the observations, which I think was really delved into a little bit later with the soft margins. But I thought maybe that's also something to consider with this use case, this model use case overall, that it's not something you like, which is impacted by the whole of the data more than a subset. That was quite interesting. But what was a takeaway is that, not necessarily a takeaway, but something that I thought was not even a limitation, but the first thing that popped up in my mind, obviously, was that, real world data is not so clear cut that you are going to be able to always put your data into neat classes as such and divide them into those sections, so to speak, which comes under the non-separable case in the book. And we can't always apply this same solution to the optimization problem. And actually, because it relies only on a small subset of the data, I think maybe you run the risk of that hyperplane, the maximal margin hyperplane being very, very sensitive to a change in a single observation. Because if you shift one observation just even slightly, I think, unfortunately, I didn't have time to put a visualization in, but if you shift one visualization, one data point even, or add a data point that can create a dramatic shift in that hyperplane, then I guess how robust is that as a classifier at the end of the day? I mean, it is robust, but it's sensitive. And I thought that was quite interesting to think about, and considering like how to, I guess, have caution using it, which was kind of then a segue into the soft margin approach, which I've not described very elegantly as an almost there solution, but it's one of those cases where I suppose if it's good enough, it does the job. And that is, as the name suggests, it almost separates the classes. And this generalization of the maximal margin classifier, as we saw before, is known as a support vector classifier. And it, according to the book, is used when we have very nonlinear cases where it's not so easily separated. So in this just sample, we can see there are two classes of observations as seen by the red and the blue. And we can't just separate these in a hyperplane. If I try and draw a hyperplane, let's say from even this part of the axes, it's impossible to separate them cleanly. And this is where we can use that soft margin of almost separation, and where it can be quite prudent to try on, I guess, messier or noisier data. So again, the eternal question comes in with flexibility and trade-offs, as always. So the support vector classifier does afford us some flexibility, because we can misclassify a few training observations as cat or dog, as a means to achieve like greater robustness overall to individual observations. So there is a bit of a trade-off here, and it might be interesting to think about what use cases might be better where we do accept more violations in exchange for classifier stability, and when might it not be helpful? Because I've not used SVCs before, so it would be interesting to think about when you have a specific, like, I don't know, noisy data or use case where it gets you a closer sense, but not 100% perfect idea of how to label, or not label, classify your data.
Well, I think what it's getting at in the book is if you have a very small margin in your training data, then like, who's to say that the training data is like, either you've got like a really small kind of, what would be the word, like a difference between group A and group B, like the difference between group A and group B is really small, or else maybe this training sample isn't representative of the two groups. Maybe there is some crossover, so you want to find the line. So like, say for example, like, I don't know, height of girls, like trying to decide if someone is like female or male based on height. Like, generally men are taller, generally women are smaller, but there's crossover in the middle. So it's like finding the line where you're going to get some wrong, but like, what's the line where you're classifying most correctly, I guess. And that's a very oversimplified example, because obviously there's more dimensions, I guess, when you're talking about.
Of course, yeah.
But I think that's what it's getting at, is like, when you have this overlap in the data, you want to find the line that is going to do the best for both classes.
So actually, this might seem like a stupid question. Does that line or that hyperplane, does that treat that intersection, as you say, that crossover, does it treat them as outliers per se, or is it more just, hey, there's a crossover here sort of thing, rather than commenting on the nature of the data?
In what sense does it treat them as outliers?
Yeah, I don't know how to describe it, but you know how traditionally you might see like aberrant data points that are, I don't know, like very have high variability, or are really far from the mean. Let's say in another model, we would say, oh, that's quite an outlier, let's say. Is that the same case here, or is it just that it's being classified as like as part of the intersect rather than those two separate regions?
I don't think it's necessarily an outlier. Well, like, I guess that's data dependent. Like, maybe there's some data where, like if you take the height example, you have like a 7'5" tall like female, like that's an outlier. But like 5'7" females and 5'7" men, like, they're not outliers. That's just the data distribution.
Sure.
I think that's like not a like modeling approach question, but a data question, whether something is an outlier.
Yeah, that's cool. And so actually, I guess if you were to, let's say, model those heights and you saw that there was an intersect, that is interesting information, right? Because you're looking at that intersect saying, oh, here is where these heights kind of cross over. So it's quite informative, actually, I think, maybe looking at that as well as the clear-cut classifying bits. Yeah, I thought this was quite an interesting subject over the soft margin. So yes, just a little bit more mathematical notation and some discussions on the slack variable and tuning parameters. So we are familiar with sort of the notation from before, but obviously some additions with the use of epsilon I and the tuning parameter C. So a little bit on the epsilon for context with this the formulae. So essentially, with the soft margin approach, the epsilon helps tell us where our observations lie. And epsilon I equals 0 means, or could define the observation as being on the correct side of the margin. Epsilon I, when it's greater than 1, is describing when the observation is on the wrong side of the hyperplane, or as we might say, misclassified. But interestingly enough, you also have a more another description where the observation might be violating the margin. So it's on the wrong side of the margin, but the correct side of the hyperplane. So you have instances where I think there's a visualization here which might be better suited to describing it than me just blathering on, and I can try and include it next week. But it's got quite nice observations where, like, let's say observation 2 is on the margin and observation 1 is on the wrong side of the margin, and it's quite visually distinct. But I'll try and pop that into my documentation next week. But yeah, did anyone have any comments about the soft margin or support vector classifier so far in regards to like the comparison to that of the maximal margin classifier? I'll have a look at the juicy bits with the tuning parameter C, which is, I think, where we start having more discussions about bias variance trade-off. So obviously we know that in these instances, M is the width of the margin is the margin. And it's interesting because theoretically, when it comes to the soft margin, according to the book, we would want to make the width M, as, I guess, large as possible. And because I guess then it will account for those intersecting data points a bit better. And when it comes to C and tuning, the tuning parameter, obviously later down the line, we can see in the lab work, you calculate it by, discover like the best choice through cross validation. But in general, the parameter C can be used to tweak this margin width. So if you have a larger C, you might have a wider margin, which obviously theoretically has a higher tolerance for violations. You have a higher tolerance for observations being in that soft margin space. So as a result, your model might have higher bias and no variance. Whereas a smaller C, you have less tolerance for violations, and you have narrower margins as a result. So again, I think it all comes down to the question of, the data you have, data question, and also the research question at hand when you're working with this kind of this parameter tuning. Because if a margin is very wide here, you have many observations that violate the margin. And as a result, you have a lot more support vectors, because observations that lie on the margin or those that violate the margin can affect the hyperplane, and as a result, the classifier we obtain. And the book defines these as support vectors. And they affect our support vector classifier. So the observations that lie on the correct side of the margin don't impact a classifier whatsoever. But it does mean that changing the position of an observation can only impact a classifier if it's on the wrong side of the margin or it lies on the margin itself. So the more support vectors we have, essentially, the greater to which we change our classifier. So when you have wider margins, you have more support vectors, which means obviously you're going to be altering that the classifier a lot more. And smaller C means you're not going to have as many support vectors in your vector space. So as a result, we can have a little discussion point regarding support vectors and how it affects the classifier. So we can think a bit more about parameter C's role in the bias variance trade-off. And I know we've discussed, yes. the answer is yes, it would change the number of support vectors. But in more of a practical conceptual use case, if you have noisy data, research question dependent, would we prefer a larger or smaller C, or are there instances where we might prefer one over the other, and why? I guess it depends if we want a classifier highly fit to the data, no? Like lower bias.
Yeah, I'm not sure. I haven't read this part yet, so I'm not.
No worries. This is the end of it, so as in for this week. But we can start from next week on this question, so everyone can read up to it and catch up, and we can discuss it a bit more. But that's part one of support vector machine classifiers so far. So obviously happy to discuss in detail about anything people thought was interesting, or if they've used any of these classifiers before, or if they have thoughts on the classifiers. Happy to discuss, because I haven't used them before, but it was interesting reading the chapter.
Yeah, I mean, I definitely, your presentation was very polished, so I think that will help me as I go through this.
Oh, Corey, that's very kind of you. Thank you.
I do wonder, like, why would I use this classification method versus like all the other classification methods? Especially, I don't know, the rigidity of the hyperplane kind of approach, even with the soft margin, seems like a disadvantage. I don't know. I guess these perform relatively well, so maybe I just don't understand it, but that's kind of what I'm thinking about in the high level stuff.
No, of course, completely. That's sort of what I was actually thinking of as well. Like, of course, it's not so much as you say, oh, it's good versus bad. It's more about, okay, when, appropriate use. And actually, I thought the same thing. I thought, okay, so it obviously works well in X number of cases. But yeah, no, definitely the rigidity of it definitely crossed my mind. I think as well, as we get more into the later chapters next week with support vector machines, when there are non-linear decision boundaries, it gets quite funky, which is exciting. And I guess there's more leverage to play with there. But no, 100%, I thought that too. But yeah, I thought it was interesting.